Hello and welcome to this A-level chemistry video about aldehydes and ketones. I'll start by taking a look at the structure and the bonding and the nomenclature for aldehydes and ketones. From there move into the different chemical tests that you need to know about and finish by looking at the nucleophilic addition mechanism, including two examples of that mechanism and some intricacies about each of them that you need to know. Aldehydes and ketones are similar families of organic molecules that both contain the carbonyl functional group. And the carbonyl functional group is a double bond between a carbon and an oxygen atom. And in more detail, this is made up of a single bond, sometimes called a sigma bond, and that's one of the pairs of electrons. And that's where the electron density is between the two atoms. And then a pi bond makes up the double bond, and that is where the electron density is slightly above and below the functional group. And this gives us 4 electrons in total in 2 pairs. Even though there are 4 electrons in this double bond, in terms of VSEPR, both of the electron pairs of a double bond are considered together to be one single electron cloud. And since carbon has 4 valence electrons and 4 bonds, the carbonyl carbon will have 3 electron clouds around it, and these electron clouds will repel each other equally, and so they will have a bond angle of 120 degrees all the way around this molecule. And so they will have a trigonal planar shape around that carbonyl carbon, but the rest of the molecule is unlikely to be planar. Aldehydes have got a carbonyl group at the end of a chain, and so the carbonyl carbon will have a bond to a hydrogen atom, guaranteed, and then probably to a carbon atom for the rest of that chain, but in the case of methanol, the carbonyl carbon is simply connected to 2 hydrogen atoms. Ketones have got a carbonyl group inside a chain, and so that means that the carbonyl carbon is attached to 2 additional carbon atoms. Even though it looks like aldehydes and ketones have got the same functional group, the fact that for aldehydes the carbonyl group is at the end and for ketones it's in the middle, this means that they are in fact functional group isomers, which is a type of structural isomerism. And that means that aldehydes and ketones of the same number of carbon atoms will have the same molecular formula and the same general formula, CnH2nO, but they will have different structural formulas. Aldehydes and ketones both contain the carbonyl functional group, but since the group is in a different position for both of them, there are different naming conventions. The core rules for naming the length of the carbon chain is the same for all types of organic compounds. So for instance, you have a prefix, which will be methan, ethan, propan, butan, pentan, etc. And this indicates the number of carbon atoms in the main carbon chain. For instance, 1, 2, 3, 4, 5, for those examples that I've given. And then for aldehydes, aldehydes always have the suffix al. So that means their name will always end in al. And so the shortest aldehyde would be methanal, which has got hydrogen atoms attached to the carbonyl carbon and is the only fully planar aldehyde. And then with a second carbon, we've got ethanal, and then propanal as the chain lengthens, butanal, pentanal, etc. When we have branches for our aldehyde, the carbonyl carbon is always given the highest priority, and the aldehydes have got the carbonyl carbon always in position number 1. And so that means that when you're naming a branched aldehyde, you don't need to number the aldehyde functional group. And so if we had a molecule like this, we would need to work out what the longest carbon chain is, and this molecule has got 4 carbon atoms in its chain, so this is going to be butanal. And we've got a chlorine branch to this chain. The carbonyl carbon is carbon number 1, this chlorine is in position 3, and so this molecule would be 3-chloro-butanal. Ketones always have the suffix -one. And since a ketone needs to have its carbonyl group in the middle of a chain, the smallest ketone possible is propanone, where you've simply got one methyl group either side of the carbonyl carbon. And then as the chain lengthens, we would have butanone. And it's only when we get to pentanone that we need to include a number for the position of the carbonyl group. For pentanone, there are 3 carbons that are not at the ends of the chain, and since it could be that that carbonyl group is either in the second one along or the third carbon along, we do need to differentiate. So I've drawn here pentan 2-one because we number from the end that keeps our carbonyl group closest to an end, and so this carbonyl group is on the second carbon from an end. If it was in the next position along, that would be pentan 3-one. When we have branches or other groups attached to a ketone, the carbonyl carbon is always given the smallest possible number. And so for this example that I'm showing here, we've got a chain of 4, so this is going to be butan. There's also a bromine atom attached to the carbon chain, so we've got a bromo side chain. Now, we need to give our carbonyl carbon the smallest number possible, and so we count from the end that it is closest to. And so the carbonyl group is on carbon number 2. And that puts the bromine in position number 3. And so that means that this molecule would be 3-bromo-butan 2-one. And this might seem that it is unnecessary because the carbonyl group has to be on the other carbon because it couldn't be on the same one as the bromine, but the IUPAC naming rules for clarity and for precision purposes require that too in cases like this. So it's really important that we include it. Aldehydes are readily oxidized to form carboxylic acids, and a general equation for this would have an aldehyde, and this is a general formula for an aldehyde, reacting with some kind of oxidizing agent. And when you write oxidation equations, you can just use a capital O inside square brackets to symbolize the oxygen from the oxidizing agent. And then it turns into a carboxylic acid. And so we've got an R group with the carboxylic acid functional group COOH. Ketones, on the other hand, cannot be easily oxidized in a simple test tube reaction, so therefore a chemical test to distinguish between aldehydes and ketones involves adding an oxidizing agent. There are a lot of different oxidizing agents that we could use, but there are 2 solutions that are more sensitive and more specific for identifying aldehydes, and so they are more commonly used. And the first example of a chemical that we can use to test for the presence of an aldehyde is to use Fehling solution. And so we would take a bottle of Fehling solution and we would take our samples that we think might contain an aldehyde or a ketone, and we would add a small amount of Fehling solution to both of them. This reaction needs to be heated, so we will put the test tubes into a water bath containing hot water. We definitely wouldn't use a naked flame to heat these chemicals because they are typically highly flammable. Fehling solution is a blue solution containing the copper 2+ ion. And when it acts as an oxidizing agent, it takes electrons from the substance that it is oxidizing, and therefore it is gaining electrons and it itself is being reduced. And remember, that is one of the definitions of an oxidizing agent. In terms of electrons, they are electron acceptors. And so this copper 2+ gains electrons and it turns into copper 1 ions, which are solid. And therefore we get a precipitate, and this is a brick red precipitate of this copper 1 compound. Now, it isn't copper 1 ions by themselves. We make a brick red precipitate of copper 1 oxide. And so the copper is 1+, but we've actually got a compound of Cu2O. Now, this conversion will only happen with aldehydes, and so if we see a brick red precipitate forming, we know that that solution had an aldehyde before we added the Fehlings to it. And if we don't get a brick red precipitate, if we see no visible change, that means that we had a ketone because we weren't able to oxidize that ketone using the Fehling solution. We can use the oxidizing agent Tollens reagent to distinguish between aldehydes and ketones, since aldehydes are readily oxidized to carboxylic acids and ketones cannot be oxidized in test tube reactions. To do this, we take a bottle of Tollens reagent and we add some of it to our samples that we think might contain an aldehyde or a ketone. We then transfer these test tubes into a water bath containing hot water, definitely no naked flames, and we leave the test tubes for a few minutes for the reaction to occur. Tollens reagent, before we start, is a colourless solution of silver nitrate dissolved in aqueous ammonia. And when we heat it with the aldehyde is oxidized and the Tollens reagent is reduced. And the complex ion of AgNH32 plus gains electrons and so gets reduced. That's what oxidizing agents do. They gain electrons, they accept electrons, and they turn into solid silver, which has got no charge, and aqueous ammonia. And it's the solid silver that gives us an observable change, and we see the formation of a silver mirror. And so if we see a silver mirror forming, that means that we had an aldehyde in our test tube. But if we don't get the formation of a silver mirror, if there is no observable change or no visible change, that means our substance in the test tube was a ketone, because the ketone cannot oxidize and it cannot interact with the silver in the Tollens reagent. The nucleophilic addition mechanism occurs when there is a reaction of an aldehyde or a ketone. And so this is something that's got a carbonyl group, which is that C double bond O, by itself, and so not with any other reactive atoms as part of its functional group. Remember that the word nucleophile is taken from the fact that the nucleus is positively charged, and so a nucleophile is positive seeking, and so that means that we've got something that is either negatively charged or partially negatively charged, and we might write delta minus to symbolize this. And so what happens in a nucleophilic addition mechanism is that a positive seeking species, the nucleophile, joins on to the carbonyl carbon atom. And the reason that this happens is that the carbon in the carbonyl group is partially positively charged, or delta plus. And this is because it's connected to the highly electronegative oxygen atom, which is more electronegative than the carbon, and so we get what's referred to as a negative inductive effect, where the electron density in the double bond between the carbon and the oxygen is pulled towards the oxygen atom, leaving the oxygen delta minus and the carbon delta plus. And so a nucleophile, that's something negative or partially negative, remember, attacks that delta positive carbon atom and forms a new bond to it. There are two examples of nucleophilic addition that you need to know, and they are the reduction of aldehydes and ketones to form alcohols, and to do that we use NaBH4 in aqueous solution, and that allows us to convert an aldehyde into a primary alcohol and a ketone into a secondary alcohol. And there's also the preparation of hydroxynitriles using KCN as the source of our nucleophile, followed by the addition of dilute acid in a solvent, which is usually water. In the alcohols topic, we learn that we can oxidize primary alcohols into aldehydes and secondary alcohols into ketones. With the nucleophilic addition mechanism, we can reduce an aldehyde and turn it into a primary alcohol, and we can reduce a ketone and turn it into a secondary alcohol. In order to do this, we need to use a reducing agent, and the one that we use for the reduction of carbonyl compounds is sodium borohydride, or sometimes called sodium tetrahydridoborate, but you can just use its formula NaBH4. Sodium borohydride is an ionic compound, And when it is dissolved in water to make an aqueous solution, it is a source of the hydride ion. And so it's really important that we know that the condition for this reduction is to use a water solvent. You need to be able to understand and recreate the mechanisms for the reductions of aldehydes or ketones back into alcohols. And these are called nucleophilic addition reactions. And the hydride ion from the reducing agent is the nucleophile. You need to remember that within the aldehyde or ketone, the C double bond O is polar, and that's because the carbon is electron deficient and the oxygen is more electronegative. And so the delta positive carbon is attracted to the hydride ion. And so what happens is the hydride ion attacks this slightly positive carbon atom and uses its lone pair to form a new bond between the carbon and the hydride ion. And that's down to the attraction between the two of them. This happens very readily. And that's what this first curly arrow is showing, the formation of a new bond between the carbon and the hydrogen. This would give the carbonyl carbon 5 bonds. It can only have 4. And so what happens is the bond between the carbon and the oxygen partially breaks. 2 of those 4 electrons are pulled by the oxygen away from the carbon, and the oxygen keeps them for itself. And that's what this second curly arrow is showing. Just as a note of caution, if you end up drawing your diagram a little bit too small, like I've done here, I choose to deliberately exaggerate the curl of that curly arrow, just so I can really demonstrate that it is starting from that double bond between the carbon and the oxygen and finishing at the oxygen, which is taking both of those electrons from that bond. This gives us a negatively charged intermediate because the negative hydride ion has added onto the aldehyde or the ketone, and we need to conserve the charge between stage 1 and stage 2. And that means that the oxygen that took both of those electrons from that double bond to the carbon is now going to be negatively charged because the hydrogen is now neutral because it used that pair of electrons to form a new bond. And so the final stage of this mechanism needs to show how we get from our negatively charged intermediate to the alcohol. And what needs to happen is the oxygen within this intermediate that is now negatively charged uses its lone pair to form a new bond to a hydrogen ion. And that's what this third curly arrow is showing, the formation of a new bond. Typically, that hydrogen ion is going to come from the solvent, from the water that the sodium borohydride was dissolved in. But sometimes we might choose to add a weak acid separately as a source of the hydrogen ion. And this will then produce our alcohol product, which, if we've been commanded to draw the mechanism, we don't need to show. But I'm showing it here just so we can see the full journey from aldehyde or ketone to alcohol. So I've been really generic with this mechanism, just using R groups to finish off the molecule. If we make this into ethanal, that means we'll have a CH3 group for the left-hand side R group and just simply a hydrogen for the right-hand side R group. That will, of course, then have a knock-on effect in the intermediate. It would look like this. And then the product that we produce would look like this. And so we can see that we started with ethanal and we've produced ethanol. And we could, instead of showing it as a mechanism, or maybe as well as that, we could represent this with an equation which uses structural formulas. So ethanal has got the formula CH3CHO, and ethanol is CH3CH2OH. And then to show the reduction, we are in fact allowed to just use a capital H for hydrogen inside square brackets to show that we are giving hydrogen from some kind of reducing agent without using the reducing agent's full formula. Just like we can do the same with a capital O for oxidation when we're using an oxidizing agent. And then to balance this, we actually need to put a big 2 as our coefficient in front of the hydrogen from the reducing agent, because the aldehyde is gaining 2 hydrogen, 1 from the nucleophile and 1 from the solvent. And if instead of using ethanal, we used propanone, we would have 2 CH3 groups either side of the carbonyl group at the beginning, which means we'd need to have 2 CH3 groups in our intermediate and 2 CH3 groups at the end. And so this time we would produce propan-2-ol. And we can show that in a second equation. We've got the structural formula of propanone, we've got propan-2-ol, and we're going to be needing to once again add 2 hydrogen from our reducing agents. That is always the case in nucleophilic addition. For reduction, we need to add 2 hydrogens from the reducing agent to turn our carbonyl compound into an alcohol. The nucleophilic addition mechanism can be used to produce hydroxynitriles. And hydroxynitriles are a family of organic chemicals that have got 2 distinct functional groups. First of all, we've got the nitrile functional group. And within the hydroxynitrile, the nitrile has got the highest priority because of that triple bond between the carbon and the nitrogen. And so that means that the carbon that is attached to the nitrogen is always treated as carbon number 1. There's also a hydroxy group, and this hydroxy group is always on carbon number 2. And because the nitrile has the higher priority, we refer to this as a hydroxy group rather than an alcohol group. And after that, the length of the carbon chain is what determines how this molecule is named. And so if we had a chain of 3, so we had a CH3 group in the position of this R group, we would refer to this as a nitrile, highest priority. The chain of 3 includes the carbon as part of the nitrile functional group, and so this is propane nitrile. Remember the convention that we need to have a vowel between 2 consonants in something's name. And then the hydroxy group is on carbon number 2, and so this molecule would be 2-hydroxy propane nitrile. In order to produce the hydroxynitrile, we need to react our carbonyl compound with potassium cyanide, which is an ionic compound, so in an aqueous solvent, which is what we use, it will fully dissociate into the cyanide ion, Cn-, and the potassium ion. And this, remember, needs to happen in aqueous solution, so it will dissociate readily. And then we need to follow this addition of potassium cyanide by the addition of dilute acid, which is the source of the hydrogen ion, which is needed for the second step of this mechanism. And so if we look generally, first of all, at a carbonyl-containing compound, we've got a trigonal planar arrangement around that carbonyl group because there are 3 electron clouds repelling each other as far apart as possible. So that is a 120-degree bond angle. The first thing that happens in this mechanism is the cyanide ion, which is negatively charged, attacks the partially positive carbon atom in the carbonyl group. And so it uses the lone pair on the carbon atom within the cyanide ion to form a new bond between the carbonyl carbon and the carbon from the cyanide ion. And then this has a knock-on effect because the carbon that is in the carbonyl group would have 5 bonds if that was the only thing that happens. And that can't be the case. And so what happens is one of the pairs of electrons from the C to O double bond is pushed onto the oxygen from within the carbonyl group. And so that bond breaks partially, and so it's going to become a single bond with only 2 electrons in instead of a double bond with 4 electrons. This then moves into the formation of a negatively charged intermediate, which is mostly those 2 reactants bonded together. But because we need to conserve the charge from one stage of a reaction to the next, the oxygen that took that pair of electrons from the carbonyl double bond, it needs to be negatively charged because now the cyanide is neutral. And then to finish this mechanism off, the oxygen with that negative charge and the lone pair of electrons that it took from out of that carbonyl double bond attacks a hydrogen ion from the dilute acid. And this is the formation of a new bond between that oxygen and the hydrogen from the acid. And this then produces something that is neutral because we had two charged particles in our intermediate, one negative, which we must show in a mechanism, and one positive, which we also need to show. And we produce our 2-hydroxynitrile. Now, if in this mechanism we had used ethanal, that means we would have had a CH3 group in place of one of these R groups and a hydrogen in the other position. That means our intermediate would have looked like this. Again, we're just literally swapping those R groups out and the CH3 and the hydrogen in. And we do the same with the product. And you can see, in fact, that the first product that we have made is the 2-hydroxypropane-nitrile from before. And we can represent that with the equation, with the ethanal in its structural formula reacting with the potassium cyanide in aqueous solution, remember, and then that converts into the 2-hydroxypropane-nitrile and the potassium ion, which I'm including here because I'm using the full reagent in the reactants, but technically that potassium ion is a spectator ion because it's aqueous on the left and aqueous on the right. And the dilute acid, the H+, would also be added over the arrow, and that would be aqueous as well. I suspect you wouldn't be asked to include state symbols in an equation like this, and the reason is that the organic compound, that aldehyde or ketone, might be soluble in the aqueous solution or it might not. The solubility of organic compounds, particularly carbonyls and alcohols and things with polar functional groups, that solubility depends on molecular size, with the longer groups becoming less soluble. So ethanal is likely to be soluble, whereas something longer, say hexanal, is likely to be insoluble, so it would have the liquid state symbol. But as I say, I suspect state symbols not required. If we did this mechanism on propanone, a ketone, we'd get a very similar reaction pathway. We're just swapping that hydrogen for a methyl group, and that's the same in the intermediate and the same in the products. But this time the product would have a different name. It would still be 2-hydroxypropane-nitrile, but we also have a methyl group on that second carbon atom. And so this would actually be called 2-hydroxy-2-methylpropane-nitrile, remembering that our branches need to be in alphabetical order. And then an equation for this reaction would look very similar to the aldehyde reaction. The only two changes are we're showing the structural formula for propanone instead of ethanal, and then we're showing our organic product as being slightly different to the 2-hydroxypropane-nitrile. Now you can see that I'm giving priority to the nitrile by putting that in its normal form, and the methyl group along with the hydroxy group are shown as being in brackets. You could probably get away with that from the other way around, but I prefer to show the nitrile as being part of the core chain. That reminds us of its priority. When we do this mechanism, we use potassium cyanide, which has some associated hazards. And so it's really important to carry out a risk assessment. And so the hazard identifies the chemicals that could be dangerous or the parts of a practical that could be dangerous. And so in this case, potassium cyanide is the hazard. And then the risk tells us the nature of the hazard. Well, potassium cyanide is toxic, and it also produces hydrogen cyanide in the reaction. And so we need to take steps to minimize this risk, and this is by considering the control measures. Well, the toxic nature of potassium cyanide can be offset by storing it and handling it carefully. But the production of hydrogen cyanide is more of a danger, and so we need to make sure that we do this reaction in some kind of fume cupboard to prevent that hydrogen cyanide being released into the main part of the room. In addition, this mechanism produces some organic products which are flammable, and so the control measure here is to heat this reaction if you want to warm it to increase that rate of reaction, heat that up in a water bath or with a heating mantle definitely no direct flames. As an alternative to using potassium cyanide as our source of our nucleophile, we can actually use hydrogen cyanide instead. And when this reaction happens, the mechanism is exactly the same as for the potassium cyanide because we're still using the cyanide ion as our nucleophile. And the equations are really similar as well. There are a few key differences. Of course, the first one is that we're using hydrogen cyanide and we need to represent that in the equation. The second difference is that we aren't producing potassium as a spectator ion in the products. And then the third difference is we actually don't need to add an acid to our equation, and so we don't have H plus over the arrow. And the reason for this is that the hydrogen cyanide can be the source of the hydrogen ions as well as the cyanide ions because it is weakly acidic and it will dissociate into H plus ions and the cyanide ions as well. Overall, though, despite the toxic nature of KCN, KCN is preferred as the source of the nucleophiles because it is an ionic compound, which means in aqueous solution it will readily dissociate and produce a higher concentration of cyanide ions than you'd get with the HCN, which is only weakly acidic, so will only partially dissociate. In addition to that, hydrogen cyanide is a gas, so it is much harder to handle and store than the KCN. So overall, KCN is definitely preferred. When you carry out nucleophilic addition reactions on aldehydes and unsymmetrical ketones, for instance, ethanal or butanone, you produce a mixture of enantiomers. Having two enantiomers means that you've got two molecules that are mirror images of each other. But more than that, they are non-superimposable when you turn one of them around. Another way of referring to enantiomers is to call them optical isomers. And you get optical isomers when there is at least one chiral carbon within a molecule. And a chiral carbon is a carbon atom in the molecule that has got 4 different groups attached to it. And these optical isomers will rotate plane polarized light, either in a clockwise direction or an anti-clockwise direction. Even though this mechanism produces 2 enantiomers, there is no overall optical activity, as the product is a racemate, sometimes known as a racemic mixture. And this is where you have an equal mixture of the 2 different enantiomers. And so there is no optical activity, since the rotation of plane polarized light, either clockwise or anti-clockwise, will cancel each other out precisely. This racemic mixture comes about since the molecules with the carbonyl groups are planar in the region around the carbonyl carbon. And so this means that when the nucleophile attacks, the cyanide ion in this case, the attack is either going to be coming from above the carbonyl group or below the carbonyl group. And since both of these attacks are equally likely, you will get 50% of the nucleophilic attack occurring from above the carbonyl group. And this will produce one of the 2 enantiomers, and 50% of the nucleophilic attack occurring from below the carbonyl group. And this will produce a different enantiomer. And this means that we end up with an exactly 50-50 attack angle, and so we end up with an exactly 50-50 mixture between the 2 potential enantiomers that could be produced as a result of this nucleophilic attack.